In this presentation, we will be going over Heron's formula and sine function being used to solve the area of a triangle. Now, Heron's formula and the sine function are both different in the way they use values to find the area, but they're both fairly similar. Heron's formula and the sine function are both very similar when finding the area of a triangle. They're both used to find the area specifically when the height, the altitude of the triangle, is unknown. On the other hand, the actual formulas are very different. The sine function uses a derivation of the sine function to ultimately combine the sine function with our known triangle area formula, which is 1/2 base times height. Now, Heron's formula, on the other hand, uses what's called the semi-perimeter, which is denoted by the side lengths combined divided by 2. This is obviously different than the sine function's formula. The same parts that determine a triangle also determine its area, so its side lengths, its angles. In the case of having two sides and an included angle, there is a simple formula in terms of those parts. Based on the above diagram, which was used in explaining the law of cosines, each triangle has a base of value c, an altitude of value b sine of a. Using this information, we get this formula derivation. The standard area formula is technically 3 formulas that all are used when subbing in different values for whatever side lengths you may have. Little a, b, and c represent each side of the triangle. Big A, B, and C represent the angles. This formula is used for side angle side when only 2 sides and 1 included angle are known. The biggest difference between this formula and Heron's formula is that the Heron's formula is used for side, side, side when all 3 angles are known. This diagram down here on the left basically goes from our 1/2 base times height model, which is our basic triangle area formula, then subbing in our side length c and altitude b sine of a, and then just simplifying down to 1/2 bc sine of a. And also over here on the right is a cleaner diagram of the 3 formulas that are interchangeable when solving for your area of your triangle. Obviously changing out a, b, or c as your angle, depending on which angle it is in the triangle you're using, and making sure that that angle is included between the 2 side lengths you're using. Notice that angle A is used with sides B and C, angle B is used with sides A and C, and angle C is used with sides A and B. This obviously being because you don't have the value of the other side. So you're using the height to determine the area of the triangle. Now, for examples using the sine function to find the triangle area, we're essentially going to just use our equation that we've just discussed. Now, to find the area with sides A 15, C 10, and angle B 49 degrees, it's pretty simple. Multiply the base with side C, you get 150. Multiply this by sine B, which B is 49 degrees, giving you 113.2. Then you divide this by 2, giving you 56.6. Now, finding the area of a regular octagon with 8 equal sides and 8 equal angles, inscribed in a circle of radius 9 inches. First, we'll just split the octagon into 8 congruent triangles. Then you want to determine that it is 45 degrees for each included angle on each of these triangles. Then, using the formula we just found to solve for the area, we just found that area equals 1/2 your two side lengths multiplied by the sine of the included angle, which in our case is 45. This ultimately gives us 28.64 inches squared per triangle, which, when multiplied by 8, rounded to the nearest tenth, gives us 229.1 inches squared. Now, in a more simpler fashion, which you probably won't see on most assessments, you can just find the area of a triangle. This is rather simple. You're just given two side lengths, an included angle, no extra shape, no extra this or that. Essentially, you just plug and chug. You put your two side lengths, your angle in, you simplify, and you get 62.4 units squared. Now, Heron's formula uses something a little different. We mentioned before that it uses semi-perimeter, which is the three side lengths, A, B, and C, added together and then divided by 2. This is used when the three sides of a triangle are known, and obviously not the height. That would make things a lot easier. Then, using the semi-perimeter, you multiply the semi-perimeter by values that are the semi-perimeter minus each of the sides in 3 separate values. Now, the law of cosines is used for Heron's formula. The law of cosines is not in the actual formula, but it's used in the proof to create Heron's formula. The law of cosines is similar to Heron's formula because it's used when two sides and one angle are known. However, the angle that is known identifies which formula to use. Now, this big hunk of a proof is essentially a lot of algebra and trigonometry to figure out our equation at the bottom of s multiplied by s minus a multiplied by s minus b multiplied by s minus c. Now, a few key things to note besides multiplying by 4 here and 16 here are when we go from sine squared c to 1 minus cosine squared c. Now, this is a simple Pythagorean identity, which is just simply that. We also use, as mentioned, the law of cosines to turn 2ab cosine c into a squared plus b squared minus c squared. Then we use difference of squares. Difference of squares again. Again, this is just a lot of heavy algebra. Then ultimately, we end up dividing out 16 down here, which ultimately gives us our overall formula, which we will now use. Using this newfound formula, we can find the area of a triangle given its 3 side lengths. So if, per se, we're given the side lengths 13, 15, and 18, we can do just that. So first, we're going to find the semi-perimeter, which you just add the 3 sides together, divide by 2, giving you 23. Then we use the formula. You multiply 23 by each of the 3 values that are the semi-perimeter of 23 minus a, b, and then c. This gives us 20 radical 23. So the approximate area is 96 square units. Now, this problem it's a lot of words, but essentially it boils down to using Heron's formula as part of a problem. So Because deer require food and water and cover protection from weather and predators and living space for healthy survival, there are natural limits to the number of deer that a plot of given land can support. Deer populations in national parks average 14 animals per square kilometer. If a triangular region with sides 3 kilometers, 4 kilometers, and 6 kilometers has a population of 50 deer, how close is the population on this land to the average national park population? We can find the area of the land region using Heron's formula, simply by adding our sides 3, 4, and 6, dividing them by 2, and getting 13 over 2, and then simply putting 13 over 2 into our equation with our 3 side lengths, 3, 4, and 6, giving us our area of 5.3 kilometers squared. Now, if this land were to support 14 deer per kilometer squared, it would have 14 multiplied by 5.33, or about 75 deer. So, if this plot of land, we're saying, would support the average amount decided by the national parks, we would have 75 deer, but we don't. The problem tells us that we have a population of 50 deer. So, the population on this land of deer is less than average by 25.